All right. More advanced polynomial division. Here we go. If I can find my pen, there's my pen. All right, now what we are dividing by, we're now dividing by something more than just a linear polynomial. We're now dividing by higher degrees. And so it's a lot of the same rules of the division we did before, but it's a little bit deeper of a table. So here we go. Whatever you are dividing by, you're going to put that down this left column. And you want to make sure to account for each degree on the way down. When it comes to division, you are best off if you put placeholders for any terms that aren't there, which I'm going to talk about in the second example. Now, this entire polynomial that is being divided, called the dividend, needs to go in the interior of these boxes. We start off with the largest degree term goes in the upper left corner. And then it begins. What do I multiply 3x squared by to get 6x cubed? And I'm looking in chat. What do you multiply 3x squared by to get 6x cubed? Good, 2x. And now that I have that, you can probably see that you can now figure out what goes in these two boxes. So multiply to get those two boxes. (2x multiplied by negative x is and then 2x multiplied by negative 3 . Now, this diagonal has only two boxes. I need to have those two boxes add up to make 13x squared. I have this negative 6x down here, and you want to be aware that that box plus two more along this diagonal, all three of these, let me emphasize by highlighting, these three all together are going to add to make negative 11x. But the thing is, you're going to do one degree down at a time. We first just took the 6x cubed and wrote it down. The next thing we're working on is x squared, and we only have one other box to go in. And correct, 15x squared, that is exactly what you want to add to negative 2x squared to get positive 13x squared. And once you have the top of the interior, you're ready to figure out the next term in the quotient. What's going to go here is going to multiply by 3x squared to get 15x squared. Now, from previous experience, you might remember that once I get that constant term of my quotient, that draws a line. And anything that occurs in the interior after that is a remainder. So let's see how this goes. You can now fill in 2 boxes. Five times negative x, 5 times negative 3, now, like I said when we finished this first column, the terms that are going to add up to make negative 11x are going to come from this diagonal along here. So far I have negative 6x plus negative 5x, and I'm trying to get negative 11x. It looks like I don't have anything else to add to that. So I don't have an x term in my remainder. If you want, you can write 0x, but you don't have to write anything at all because nothing is there. Then I need to account for my constant term. And with that constant term, I can look at if there was a remainder, I would put it here. But along this diagonal, negative 15 is all I needed. So this is 0 for the remainder. Yes, I am recording. The quotient is the result of that division. And so I see a question. Why is this right here a 0x? Each, in the interior of the box, I have to be able to add every box together and get this polynomial. So what I did was I color-coded it by degree. And each degree goes along an addition of these diagonals. If you set this up where you have every degree term written down 1 degree at a time. So when it came to the x's, I needed to make negative 11x when I added these 3. And after doing the division, I found that I already had negative 6x plus negative 5x. And I was looking at what else do I need to add to make negative 11x, and I don't need to add anything. And I don't have to write down 0x. I only wrote that down to emphasize that you do have to think through the addition of that diagonal and figure out if you have 0 remainder for that particular term, or if you have something of that is a remainder. And then also when it came to the constant term, we saw that we were able to get all of this polynomial that was being divided in the interior without having to bleed over to the remainder. And I hope that answers your question. We have a remainder of 0. And then, then I want to write, and on the homework, I decided to actually write out your p of x already because I saw how much of a pain it was. So the polynomial that you began with, 6x cubed plus 13x squared minus 11x minus 15, that p of x is equal to, this is for the divisor. The divisor is what you divide by. So that's the 3x squared minus x minus 3. The q of x is the quotient, the result of the division, and that is 2x plus 5 And with no remainder, you don't need to write anything. So what I want you to see is that this means that we just factored a third degree polynomial a little bit. It may not be fully done factoring, but it's through division that you're able to factor third degree polynomials and higher. If you have a quadratic, a degree 2, after seeing this, do you actually appreciate the quadratic formula and that you can actually just flat out get your solutions? With third degree polynomials, I'm giving you one solution and then it takes you this much to find the other ones, or at least as much as you were seeing in the last set of notes. Then for writing the result, in the homework, I also pre-wrote the p of x over d of x, which would be the polynomial being divided, called the divisor. No, sorry. Saying it wrong, getting my words wrong. It's called the dividend, but people don't use that word very often. And then divided by the 3x squared minus x minus 3, which is the divisor. It's doing the dividing, so it's the or, is equal to the quotient, 2x plus 5, and with no remainder, I don't need to write anything else. So it shows you this form is being able to look at how that original polynomial can be factored. This form is looking at the answer to the division. All right, ready for another one? Yeah. So here we go again. What we are dividing by, do you notice it has an x squared term and a constant, but it's missing an x term? Yeah, these can get brutal. So you want to make sure to account for every degree. You have a 3x squared. The next degree down is an x term. You don't have any. That means you want to put a placeholder of 0x. This will allow things to line up really nicely. And then plus 1. As we start the division process, we first take the leading term and put it in the upper left corner. And now we get going. What do we multiply 3x squared by to get 18x to the 4th? And what do we get? Because I just see a lot of circles with letters and faces. And a new purple hair dye, I think. 6x squared, good, thank you. Then we multiply by 0x. You can choose if you want to just put a 0 in here, or if you want to look at it's an x times an x squared, making it an x cubed. If that helps, you can either put just 0 or 0x cubed. It does not matter. But what it's doing is it's setting you up for those diagonals that are the like terms that get added together. And then 6x squared times 1. Now, the leading term is always taken care of right off the bat. Then the next degree down, these diagonal boxes need to add to make positive 9x cubed. And I'm going to erase something real quick and just ask you, if you see that that's 0, do you realize that it's part of what's making the x cubed, or do you see it better if you actually take the time to go, that's an x squared, When you multiply them, you get an x cubed, so I have 0 of the x cubes. That way, when you look at the diagonal, you have a prompt of x cubed to kind of tell you what you're trying to create. And that would be the 9x cubed. So since I have nothing so far, I need to add to nothing 9x cubed to get that term. So that's one process down. And now the next one. You tell me, what do I multiply 3x squared by to get 9x cubed? Good. 3x. So 3x times 0x. It really might help to just look at the fact that it's an x times an x, even though it's 0. So that means x squared. And that helps a lot better to see the full diagonal getting itself ready. I'm not done with that column. I now have 3x times 1 to give me 3x. And now I'm done with that column. So as we've been doing the division, the first thing we did was just write down the leading term, and that was done. Then we went 1 degree down from that and made sure that diagonal added up to being the degree 3 term. And now I'm in the middle of this diagonal that will add together to make the degree 2 term. What do I need to add to 6x squared plus 0x squared to get 3x squared? You got it. Negative 3x squared. And when I add all these together, that will give me the positive 3x squared. Now, that was my last term, but that doesn't hold on, let me start again. That was the last term of the polynomial that is being divided. That does not mean I'm done. I've still got this 3x down here, and I've got to figure out how to manage it. So here we go. What number needs to go here so that when I multiply it by 3x squared, I will get negative 3x squared? And you said negative 1. Good. Now, negative 1 times 0x. Again, you can write just 0. It does help a little bit with lining up if you look at the fact that you have just times x. And then, oh, I was not color coding the way I was. There we go. And then negative 1 times positive 1. Now, here we go. Are you ready? Are you ready? I'm going to try to erase these highlights without erasing the polynomial. Darn it. Okay. So that was 0x cubed, and that was a 9, I believe. Yes. Okay. I just wanted to erase those so I can use this color again. I have 3x plus 0x plus something else, but I don't have an x term. If I don't have an x term, that means that I have 0 x's. I've got to have these boxes add up to get this polynomial. So my x's, I have to have something that counteracts that addition of 3x. So negative 3x is what I need for this to add to this diagonal to get 0x. And then I don't have a constant. So what is the constant if I don't have one? 0. And now I need to add to the -1 something that will cause it to equal 0. And I already saw the answer, +1. Now, when your quotient hits the constant, anything that occurs after that is part of the remainder. So now what I have is a quotient of 6x squared plus 3x minus 1, a remainder of -3x plus 1, and then just finish writing these out. So I began with the polynomial. I need to be able to read it. I began with the polynomial 18x to the 4th plus 9x cubed plus 3x squared is equal to this equal sign, the divisor, 3x squared plus 1, that's coming from this. That is my divisor. Multiplied by my quotient, which is the result I just got from the division. And then finally plus my remainder. I'm going to put the remainder in parentheses. I don't have to, but just to kind of emphasize, hello, I am the remainder. So just trying to point out where all these things are coming from. What are the advantages of... Okay, so in this form, it's mostly useful if you don't have a remainder, but then again, it can be useful in other ways. Algebra is so much more language than a lot of other stuff we do in math. When we look at all this algebra on its own, it is just describing relationships. You can find yourself in different math situations where you need it written in a particular form to better work with that particular algebra, is what some of it comes down to. Is the remainder some sort of 0? No. It's really more a matter of depending on what you are working with. For some of you, you're never going to see any of this used, but some of you are going to see this in use, and you just find yourself in situations where you need to write it in a certain way so that you can go forward with your math. It's not necessarily the best explanation or most thorough explanation, but it's a lot of algebra issues. I hope that helps a little bit, but let me say again, this form is particularly nice for when you don't have a remainder because it begins the factorization. This right here is actually worth taking a moment to mention. We are about to go into the next unit, which is rational functions. And rational functions are when you have two polynomials in a division. So this by itself is a rational function. And you can rewrite the rational function to determine certain aspects about the graph. So as you study this week for your polynomial test, know that the time you're putting in is more than just for this test. It's for the entire next chapter. Anything that doesn't make sense with the polynomials is going to snowball in the next unit. So I want to make sure that this week you feel very, very good about polynomials. So the division that we began is equal to the quotient plus the remainder that was not able to be divided by the divisor. Okay, there you go. Polynomial division, that's it. Polynomials taken care of, done. And I know you've got to have questions. So I'm going to come over to, let's see, I just released the answers with homework 4.7. And this is definitely very, very important. You need to know that if you are told what one of your roots happens to be. So for this first problem from the previous homework, you were told that you were trying to figure out if 1 was a root. And you plug 1 into all the x's and just see what you get. And if you add them together, you have 1 plus 5 plus 2 and then minus 8. And you're getting 0 out of it. That means that f of 1 is telling you about a root. And that means x minus 1 is a factor. Anytime you find roots, that tells you factors. X minus the root is a factor. Then if it is a factor, you're going to do division. And when you do division, you end up getting a quotient. And your job with these problems is to factor the quotient further so that you can find the other roots of that third degree polynomial. And know that I'm only giving you these problems where I tell you what one of them is, or ask you, is this one of the roots? And you can plug it in and see that it is. You're not going to play the guess and check game. Be aware that there is a guess and check game when it comes to third degree polynomials and finding the roots. And you're not going on that guessing route. You will be given a 0 or be hinted to a 0. Then you use division and you continue with your factoring or quadratic formula to find the remaining roots. With number 2, you find out that, well, it's not a root. It doesn't give you 0. Don't you love those problems? That means you're done. And then 3 and 4 from that homework assignment ended up being roots. When I plug -3 into each of these x's, I will get 0. For number 4, if I plug 2 into all of these x's, I will get 0. And whoever shows up as a root, x minus that root is a factor. Does x plus 3 make sense? If -3 is a root, do you see that that means you're going to make the factor x plus 3? And for number 4, if 2 is a root, then x minus 2 is a factor. And your process is to go through division and then take the quotient and factor further. to find the remaining roots. And sometimes when you get to this quadratic, you will have something you can't factor and you need to throw it into the quadratic formula, and that will immediately tell you the other roots. So do you feel, is this making sense on how you factor a third degree polynomial or higher? And let me tell you, for every, yeah. Yeah. So with x squared plus x, if you were actually doing quadratic formula, you would want to realize that the constant term is 0. So that means that your a is coefficient 1, your b is also coefficient 1, and your c is 0. I will tell you that in that situation, you wouldn't want to use quadratic formula, because when you don't have a constant term, that means you can factor an x out, and that is much nicer to work with than going through an entire quadratic formula. But with the quadratic formula, then you would have to do x equals negative b plus or minus square root of b squared minus 4ac, and because c is 0, you get 0 all over 2a. And the square root ends up being the square root of 1, which is the number 1. Anytime this comes out as a nice number, that means you could have factored it. But anytime you're stuck with a square root, you weren't going to factor that thing if you have a square root with numbers stuck inside or with a negative number inside. And did the least degree, I had to rush through least degree. It's not necessarily the most important thing for you to be aware of. What you want to realize is the more a polynomial turns and twists, the higher degree polynomial is required to just make that happen. However, you also want to be aware that you could have a very high degree polynomial that just kind of goes, but steeper. You could have a very boring looking high degree polynomial. What if I asked you to graph x to the 100 power? If you just, that is a 100 degree polynomial. That a 100 degree polynomial has the potential for 99 minimums and maximums. That's a lot of turning. But if you were to graph just x to the 100, that's all right. If you were to graph just x to the 100, do you know what that would look like? And I'm preparing Desmos for you. I want you all to think, what does that look like? Are you ready? Are you ready? Here it comes. This is what x to the 100 looks like. Yeah. If you are dealing with numbers that are like between, let's just say 0 to 0.9, if you think about putting that to the 100th power, that's a very, very small number. But as soon as you get numbers larger than 1 and you put it to the power of 100, I've got to go, way out here and to see it. This is really steep, really, really steep. So if you have x to the power of n, you want to know what that looks like. If it's an even number and it's a very high even number, it looks like an extremely boxy parabola. Like somebody tried to stuff a parabola into a box and like squished. I don't know if you can picture what I'm picturing. You're like trying to push the parabola into the box and making it bend to the shape of the box. That's kind of what happens when you have an even degree lone term polynomial. But when you start bringing in some other terms, things are going to change. Let's just throw in x to the, there's minus x. Let's do minus x. Let's do to the 99. That's really boring. That didn't do a whole lot, did it? In fact, I want you to look at that. Do you see how very little effect subtracting something just 1 degree less had? That's why a lot can be determined if you look at the leading term of a polynomial. So yeah, what did it do exactly? Let me do this. I'm going to duplicate it so I don't have to keep retyping. And then I'm going to take this off. So here's x to the 100. And I'm going to color that one differently. So there's not much of a difference. How crazy is that? If I were to graph just x to the power of 99, do you expect to see something substantial? I'm going to get rid of these two and let's take a look. X to the power of 99, trying to think of what that looks like. It's like you're taking that like x cubed polynomial and forcing it to sit in a chair. And just like trying to make it fit to the chair. It is still actually a very smooth curve, but you can only tell that if you zoom in a lot that it's smooth. It doesn't look that smooth from the outset. But x to the 99 is a big deal. But if you add or subtract that with x to the 100, it's really not that big of a deal in comparison. The higher that exponent, the crazier it's going to grow. So I'm hoping that that's making some sense and creates a really fun looking graph, doesn't it? So are you still with me? Is everyone still with me? I'm still recording, so if I say anything that you want to look back on, you can. When it comes to finding the minimum degree, I mostly just want you to be aware of what a polynomial could look like. It could have relative minimums and maximums, and it could have little wiggly points, like this right here is kind of wiggly. But the more wiggles you see going on, you've got to have a higher degree to do that. Okay. each time you turn another direction, it has to go up a degree to do that. So what you're doing is you're counting how many times it changes direction and how many, and including kind of like, I like to see it as how many times it tries to change direction. So right here, it changes direction. Right here, it changes direction. It looks like it is actually changing direction right here twice, but really, really tight. If you see this as more of a wiggle, you will count it as a maximum minimum pair. So each time the graph goes wiggly like that, you have to add 2 degrees to that polynomial to make it wiggle back and forth. So if you count up the number of mins and maxes, 1, 2, 3, 4, and add 1, you get the minimum degree. For this one, you see a maximum, and then this wiggle is its attempt to have a minimum and a maximum. So that counts for 2 degrees for its wiggly attempt to break free and create some lows and highs. So 2 plus 1 is 3, and then you always add 1, but it helps to realize that it is even degree if it goes in the same direction on both ends. So this is minimum degree 4. For this one, you can tell you've got this maximum here. You can tell you have this minimum here. And what I'm hoping you can identify is this is either a little max-min pair or a wiggle trying to be a max-min pair. And the same with this over here. A max-min pair or a wiggle counts for 2 degrees worth of a polynomial. A relative minimum or a relative maximum accounts for 1 degree. And then if you add 1 to that number, that is the minimum degree of a polynomial that looks like that. Now, what you also want to realize is because the ends are going in opposite directions, you know it is an odd degree polynomial. And with how much it wiggles and turns, it is either a degree 7 or a degree 9 or 11 or 13, and I could keep going. It is an odd degree polynomial of at least degree 7. When you look at a graph, are you able to tell whether it's an even or an odd polynomial for its degree? Even, same direction on the ends. Odd does disco. Haha, because it's odd to do disco. Yeah, I'm just being silly. Now, this last piece of homework 4.7 was making sure that you understand these vocabulary words. Increasing means heading up. And from x equals -2 until x equals 0, you are heading upward. And so we are stating the x interval where it heads upward. And then when I look at the 2 to infinity, that's the x interval when it again heads upward. And then for where it decreases would be the x intervals where the graph heads in a downward way, and the other x interval where it heads in a downward direction. Now, even though I really want to point out to you, are you paying attention? Are you paying attention? This looks like a point. But there's a difference between a point and an interval. Now, there are English words that, some of you probably know this. What is the word for when you spell it exactly the same way, but it depends on its context for what it means? Who knows that word? I'm sure at least one of you knows that. When you have the same looking word. Oh, let's see, what would be an example? Oh my gosh, I don't even remember. I'm trying to think of an example of a word that's spelled the same but means different things depending on what context you are in. Ah, that's, yeah. Ooh, like, yeah, I see what you're saying. There's a variety of things. It might be homographs. I don't remember. Zest and zest. There are two different meanings to zest. Ah, thank you. You're right. And what's funny is this is just something that I realize you already realize it, I'm sure. This means either read or read, depending on just the context it's in. So, like English, math sometimes writes things the same exact way, but you have to look at the context to determine which it's referring to. So be aware that when you have a parentheses and you have numbers in them, not infinities, but numbers, you can see that here, 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 and here. If you are saying this is the x interval where it's increasing, it's referring to this region. But over here, this is the point, x coordinate -2, y coordinate 0. And those are they're two different objects. You've got one is a point, one is a line segment. So you just have to make sure you're clear that you are dealing with different meanings, even though it's written the same way. And be careful with that. And with polynomials, one thing that I don't think I've said it fully. Polynomials always have a domain of all real numbers, negative infinity to positive infinity every single time. Even degree polynomials have a limited range, but determining that range is not something I'm going to be asking of you in this class. This one was something you could look at the picture and figure out what the range was, but I'm not going to have you worrying about range on the test. I just want you to be aware that an even degree polynomial will have a limited range. The range, in other words, is not all real numbers. But if you have an odd degree polynomial and it does disco, it's got to cover the whole field vertically. So an odd degree polynomial has a range that is all real numbers. I'm not going to test you on that. I just want to point that out so that you can be aware. Okay. Ooh, I have a short quiz for you. And let me warn you ahead of time. It's all multiple choice. So let me do a quick review before I throw it your way. And I think you're going to be happy. I kept it a quick thing to do, no calculations. Yes, you have to take it. Yes. Okay. If you are told that 5i is the root of a polynomial, what also has to be a root of that polynomial? Negative 5i. If if 1 plus the square root of 3 is one of your roots, its conjugate is changing the sign on the root. If you're dealing with an imaginary complex type number, you only change the sign on the I. What? I'm not sure what you're saying, rot. The conjugated rot is just, oh, root. Yes. Yes. The conjugated root is just, you change the sign only on the awkward part. The part that has the I or the root, those have the signs different. And the fundamental theorem of algebra, you'll appreciate in a moment. It says a polynomial of degree n has n complex roots. And I'm trying to remember what else I threw in there, because I tried to make it really relatively decent. I don't know. I threw something in there that was pretty reasonable. But right now, off the top of my head, I don't remember. But it was all multiple choice, so you got a shot. Okay, I'm going to release the quiz.